free to sit wherever you want in lecture. If you guys, once I start letting you guys just check yourselves in, just go wherever you want. Because I know like where you're at may not be where you want to be at, just comfort-wise. There. Yeah, that's there's another one over there. I know there's one with staples usually. All right, let's get started. Okay, so we have to learn how to we learn how to write formulas for ionic compounds. Let's review a little bit real quick. Okay, so let's say you have cobalt 2 plus. Yeah? Cobalt 2 plus. I could have just thrown that one. And let's say iodide. So what do you, when you write the formula for an ionic compound, what do you have to do? Not just with this one, in general, what's your goal? Balance charge, right? You want to balance the charge. So you look at cobalt, it has a +2. Iodide has a -1. So what does the ratio have to be? 1 cobalt to 2 iodides, right? So that'd be COI2. But then if I have something like this, right? Then what do I have to do? How many cobalts do I need for every phosphorus? 3 cobalts, right? For every 2. She's a genius. Yeah. How did she do that? Took little charges, right? And crossed them over. Then you're going to be asking, and you don't need to write the charge, just the number. Like that. Oh, did I do that right? I didn't. I got the arrows in the wrong places. This one's like this. Like that. So you just cross it over. And the reason that works is because it's like finding a common denominator. You just cross multiply to get the same number. So what you're doing is you have 3 for here, right? 3 times 2. And then for here, you have 2 times -3. When you add those together, they're both 6. One's +6, one's -6, and then they'll cancel out. But your goal is to get that charge to 0. Okay, so now what we have to do is we have to work on naming ionic compounds. And when you name ionic compounds, the first things you have to do is identify the metal ion. If it's type 1, the writing of the name is super sort of simple. Like that. It's pretty straightforward. Right. So magnesium, right, is group 2. Now, how do I know that's in group 2? Periodic table. I look at the periodic table, it's in group 2, right? And it's type 1 then. What's the anion? It's phosphate. So the name, magnesium phosphate. That's all you have to write. Oh, I left something out there, didn't I? I wrote magnesium phosphate. All right. So here's the thing. That's the way all type 1s are done. So it's really important that you recognize which type of metal it is. Now, if it's type 2, the only way that it's different, all right, is that you insert a charge here. For type 2, you need to write the cation's charge. So that's the only way it's different, though. So the hard part is you got to figure out what the charge is in the compound. So here's one that's type 2, right? And type 2 is everything that's not type 1. So you have to know which ones are type 1 in order to do this, right? And then let's look at how we would put the name together, right? So in this case, the cation is copper 2, and the anion is phosphate. Now I know the cation is copper 2. Well, you know right now because I wrote it there. But I know the cation is copper 2 because I'm looking at this formula, right? And I see this 3 here, and I see this 2 here, right? The 3 goes with the phosphate, so the 2 must go with the copper. Okay. So that's how I know that right off the bat. So then the name just becomes this. It's copper 2 phosphate. And again, the only difference is for type 2 metals, you have to include the charge. And it's Roman numerals. Now, if it's like a written assignment or written question, and you put like the Arabic numeral, I guess that's what we call our numbers, but I don't know why, because it's not Arabic, I don't think. But anyway, whatever. Yeah, I don't care. But try to write in Roman numerals, even though you're not Roman. It's fine. All right, so I'm going to teach you this skill. It's called calculating oxidation numbers, and we will use this in the not too distant future for a lot of different things. But I'm going to go ahead and go over the other way that you could figure out that the charge of copper is 2 and copper 2 phosphate. Okay, so the charge on a monatomic ion the charge is the oxidation state or number. So if I have a 3+ ion, its oxidation number is 3+. If I have a 2- ion, monatomic ion, its oxidation number is -2. Okay? So its charge and its oxidation number is the same thing. So we have to figure out how to do those calculations. So I'm going to write copper. I've written it up here, but I just want to do it like this. I have copper 2 phosphate, like this, right? I know that if I take the charge of copper times 2, and I add the charge of phosphate, oh, sorry, those subscripts are 3 and 2, sorry. Times 2, that equals 0. This is what we're saying, like when you add up the charges, it adds are electrically neutral equals 0. That's what we mean by it's electrically neutral. If you know the charge of phosphate, but you don't know the charge of copper, you can solve that equation for x. Even though I should have written 3x the way it's written. It's more formally done up there. You can do the math. So you could say 3x is equal to, or sorry, I like to skip steps, so I'll try to avoid that. It's equal to plus minus 6 is equal to 0, so 3x is equal to 6, so x must be equal to 2. So that's how I got that number. That's like the long way of doing it, okay? The quick way, like I said, is you just look at the formula. The formula lots of times tells you, but we're going to need to be able to do this later when we calculate oxidation numbers for other compounds, okay? Oh, let me give you another one here real quick. CuO, what is the charge of copper. And we want to write its name. So when you have it and they're just like a 1 in 1, what's the charge of oxygen as an ion? 2 minus, right? So if oxygen is -2, the charge of copper plus -2 is equal to 0. So copper has to be equal to 2. So when I write the name, what is it? It's copper 2, right? Roman numeral. And then what? Oxide, yeah? Oxide. Good. I'm not going to spend a lot more time on ionic compound nomenclature. It's really important, but that's the worksheet. Today, while you're doing the worksheet, we'll straighten out like things that you're having trouble with. Make sure as you're doing the worksheet, you ask questions. Yeah, basically, that the kind of comes up, but no phosphorus is -3. Oh, sorry. I changed it up there. Okay, so this is -3. So -3 times 2, that's -6. You need to know phosphate is -3. No. -6. Yeah, but it's on the, you have to add both sides, so it's positive 6. So it's 2x equals plus 6. I think that's what it is. Yeah. It's a bad word. Are you thinking about his food? No. Okay, good. Yeah, so I think maybe you missed this little bit here. 3x is equal to -6. Added 6 to both sides, divided by 3.
So how do we get to 3x plus 6?
Because it's 3 times the charge of copper. And I just put x into the charge of copper. That's what I will. Rather than writing copper over and over. Make sense?
Okay.
Yeah. And you'll be doing it today and the worksheet. And you guys all printed the worksheet, right?
Yes.
Yeah. Half of your life. Sure.
We had a worksheet.
Shush. Okay, so another thing I want to teach you how to do is name hydrates. Hydrates, well, not all ionic compounds are hydrates, but many ionic compounds will form hydrates. And a hydrate is an ionic compound that has water attached to it and its crystal structure. So hydrates are crystalline, so they're not wet and sticky, right? It's just part of the crystal structure. So if I wanted to name copper sulfate hydrate, all I would do, right, is write copper 2, that's the charge of the copper, because sulfate's -2. Sulfate, so this is just the regular ionic compound name, and then I would write pentahydrate. I use a prefix to indicate how many water molecules are attached to the structure. Right? So the prefix 5 represents 5, and the hydrate represents 4. The prefixes that we commonly use are mono, di, tri, tetra, penta. What's after penta? Hexa. Let's see how far you guys can go. What's the next one? Hepta. Good. Octa. What's next? Nona. And what's 10? What is 10 years? A decade, so it's deca. Yeah. And then to just throw things off, there's also hemi. Hemi means it has half a water molecule attached. So for every 2 salt compounds, there's 1 water molecule holding together. So called a hemihydrate. So if you think about hemispheres, right, half a sphere, hemi just means half. Yeah, so this is 1/2. What's that? Nona, yeah. I actually know somebody named Nona, which was always funny to me. Okay, so, and there were 3 of them, sisters. Anyways, but one was 9. Okay, anyways, let's do this magnesium sulfate heptahydrate. So if I want to write the formula for magnesium sulfate, you need to write the ions out. Mg2 plus. And then sulfate's what? SO4 2 minus. And then to write the formula for this compound, I would just write MgSO4. Because they're -2 and +2, so I can just bring them together. The charges will cancel. And then I'll put a dot. It's not a multiplication, it's just a hydrate dot. And it'll be 7 H2Os like that. Now, one of the things that people will screw up, and this is kind of little aside, if I give you this and ask you to calculate its molar mass, okay, you're going to do this. Oh, well, actually, let me ask you, what do you think the common screw up is when I ask them to calculate the molar mass of this?
How many oxygens and hydrogens are?
Yeah, kind of. You know what this common screw up is?
Well, they multiply
They
magnesium.
multiply it because you see the dot, right? The MgSO4, and then they multiply it times 7 waters, and they get this mass like 49,000. I'm like, that just can't be right?
That would
This means it's attached to a hydrate dot.
Okay.
So just gonna add it all together, just like, oh. Oh, the 4 goes with the sulfate. That's part of it. Yeah, but here, just look at this. This is what you'll do. If this is 2 and this is -2, then you just get them together. The same, yeah. If you did the crossing thing, then you'd have a 2 here and a 2 here. And then you would still have to divide it by 2. Remember, it's a large.
This only is for charges.
Yeah. Sometimes it'll be even multiples too. Okay, so acids. We're going to name acids. I'm going to blaze through some of this. When you want to name the acid, the first thing you have to do is name the anion that's in the acid. Okay, so now an acid, just real quickly, the way we do them in general chemistry, in the formula for the acid, H is listed first. Okay? So in naming acids, that's anything, and I'll say H, X. X is just the anion, whatever the anion is. And there's sometimes it's 2 H's or 3 H's, but it's going to be HX. So that's the naming of the acid. Okay? When acids are placed in water, they'll produce hydronium, H3O+. Remember that ion from the memorization chart. So we know things to be acids. If you put it in water, it produces hydronium. Or if you look at the formula, hydrogen is written first in the formula. The only thing that matters in the naming of the acid is what the anion's name is. Okay? So we'll skip water. We'll do this one. Okay, let's take HF. So what is this ion? Chloride, right? So this one ends in IDE. If it ends in IDE, then you'll prefix the name with hydro and change the suffix to it, and then put the word acid after. Hydrofluoric acid, yeah. Hydrofluoric acid. Where are you familiar with hydrofluoric acid? just curious, TV watchers here. Hydrofluoric acid? No? It's, I'll give you a hint. It dissolves ceramics and glass from TV shows. It's kind of gruesome. Breaking Bad, when they dissolved the body in the bathtub, and the bathtub just like, and the body came falling through the floor, and yeah, that's hydrofluoric acid. Hydrofluoric acid will actually dissolve glass. It's nasty stuff. Oh, how did I know this? Because I looked at that and thought about what is the ion that makes. Fluoride. Well, what if it's fluorine, right? What ion does it make? It makes fluoride. So let's go like this. Let me back up for a second. Fluorine makes what ion? F minus, right? How do you know that? How do you know that? Well, that's the important part. Periodic table. Position on the periodic table will be at -1 ion.
Yes.
Here. And anytime you take the anion, and this is from end of last week's lecture. When you take the anion and you name it like monatomic, you always just change the type.
Monatomic is 1, right?
Huh? Monatomic just means one atom ion. So for these monatomic ions, for these, right, all of these become IDE. All the anions become IDE.
That's what they have one.
Yeah, just like this. Now, there are other IDEs as well, but all the monatomic anions make IDEs. Then there's like some polyatomics, and how do you know what that is? And you're just going to have to practice this. If you just do this, and you look at what's left, right? I usually tell people stick your thumb on it, don't cross it out. Just stick your thumb on it and see what's left. What polyatomic ion does that look like?
Cyanide.
Cyanide. What does it end in?
A negative.
Yeah, negative, but what is the names are, that was the hard part. What does the name end in? IDE. So if it's cyanide, again, right, it's IDE. And, huh?
The N is capital, what does that mean? They're two different.
Yeah, but this polyatomic ion, you have to recognize it, like when you cover the hydrogen, you have to recognize it as cyanide. See, it's one of the ones we memorize. So, yeah, that's the importance of having memorized it. So when you look at it, you're not thinking, well, that's a C and that's an N. You're looking at it together and saying that's cyanide.
Okay.
Yeah. So it's just practice. So that's going to be what? Cyanic acid. All right. They used to spray that stuff in fields.
That would kill people.
That kills everything.
Oh.
Yeah, farmers would kill things with it. Nasty. I'm not sure if this is true, but I had a friend whose dad was a farmer. He says they used to spray it out of crop dusters onto fields. They block off the fields and tell you, don't go in this field, we're going to spray it. And every once in a while you go in there and find a dead guy.
Was it that bad?
Yeah. The same stuff they use in the gas chambers. Yeah. Nasty stuff. Okay. The other type of ending that we have is ic endings, right? Oh, sorry, 8 endings. So we did the ides. Let's talk a little bit about the 8s. So if I say HNO3, the first thing you have to do, right, these oxo acids, is you have to get rid of this and say, what does that look like to you? What does NO3 look like? Nitrate, right? So that ends in an ATE. So NO3 minus is an ATE. So it becomes here, you substitute, right? The suffix. You don't do the prefix, just the suffix. The suffix changes the same as the IDE, but you'll put a prefix on. So this becomes nitric acid. Yeah, just because I did it as kind of a recognition skill. So, like, if you need to know what that acid name is, covered that up. Cover the height. They all have hydrogen in the beginning, and then look at the rest of it. So, if I put my thumb over the top of it here, you can't see my thumb. So I just scratched it out. Yeah. She's like, where'd you put your thumb? Oh, you can't see it. Okay, you got last type? And then we're going to practice these, okay? Let's do HNO2. All right. Again, let's do this. I'll just get rid of that part. I'll highlight it so it's not completely scratched out. So this is 8 nitrate, so this is what? Nitrites, right? So the I ending becomes an OUS ending. Nitrous acid. Like that. Nitrous. All right. So let's practice. Okay, let's do this one. I'll do this one with you, right? So what's the first thing you do? So get rid of the H, put your thumb over the H, right? Can't do it for you. And then you look at what's left, ClO2. Chlorite. H's 3 oxygens, Ite's 2 oxygens. You got to work through that whole process in your brain. So this is chlorite. So what's the name? Yeah, you go back up to here, right? Ite becomes us, so it becomes chlorous acid. Okay, so you do this one, and I'll work with this one with you. So this one over here, the HC2H3O2. Acetate. Very good. So again, you don't look at that, but you're looking at acetate. Yeah, and then H becomes what? It, right? Oops. It's bro. So this is acetic acid. That's the acid that is in vinegar. 5% acetic acid is actually vinegar, white vinegar.
Is that for you?
No. Is vinegar bad for you?
Yeah. It just sounds bad with that.
I don't know. People associate the word acid with like really bad things or drugs. Those are two things they associate it with. And it's not. It's like lots of foods, like citric acid, right?
Yeah, you're right.
Sour Patch Kids. That's the citric acid, the sourness. Yeah. Yeah, and oranges. Ascorbic acid helps with brain function. That's oxidation. There's all kinds of different kinds of acids that are good for you. You actually have a lot of ascorbic acid just floating around your brain to keep your brain from degrading. Okay. So what about HBRO? What's BRO minus? That's what it is. Is it bromate, bromite, or hypobromite? It's hypobromite. Okay. You have to remember when you do these, oh, I know this is the 8. That's 2 below. So that's bromate, bromite, and then hypobromite. Remember we talked about that rule the other day. So this is hypobromite. Oh, because the way people usually memorize it is they know the 8s because on the periodic table, like the I, the PR, the CO, the N, and the C all have 3 oxygens, and those are the 8s. So that's the starting point for most people's memorization. Then you do ites, and then if there's still less, then it's hypo. Okay. So what is this? It's an ITE ending, right? So it's hypobromus. acid. Okay. They all end in the word acid. You just throw it in there. Okay. Now H2S is a little different, but what is, because it's a diprotic acid. It has two hydrogens on it. Okay. So if I cover up the H, which I'm doing here, and you can't see there, so I'm just going to do this. Cover that up. Yeah. What is S? Yeah, and what ion name does it get? Sulfide, right? Because it's just sulfur. And it's any monatomic ion, like get rid of the hydrogens. There's only one type of atom, but any monatomic ion has I in it. And so this becomes, you would think, because it's just IDE, right? You go back here, you would put hydro and put ic at the end. Yeah. This would be hydro, that's still correct. And this is the problem. Sulfic doesn't roll off the tongue well, so they actually put the whole UR back in there. Yeah. Hydrosulfuric acid. And it turns out anytime you see sulfur in an acid, they always add that UR back in. And the same thing is for phosphorus. So phosphate becomes phosphoric acid. They add the two letters back in. I don't know why. It's archaic. But you'll have to remember that. Elaine. Okay. Writing the formulas for the acids is easier. Okay. But basically, you have to look at this and work your way backwards. You have to look at the name and work your way to the anion. So if I see hydrochloric acid, right? In fact, we just not underline the acid part, just the hydrochloric. If it's hydro and ic, it must have ended in IDE. So chloride is the anion. And then the formula for chloride is Cl minus. And then you add one hydrogen, with hydrogen ions have plus one charge, one hydrogen ion for every negative charge. So this becomes HCl. Yeah, for every negative charge in the acid, because hydrogen is plus one, you add one positive charge for every negative charge. So for like sulfide, you would add two, because it's a two negative charge, you add two hydrogen. That's where we get H2S.
So say it was a positive charge, should I just not add?
Oh, the anion will always be negative. Just by definition. It's, that second part is always the negative charge. Yeah. Okay, phosphoric acid. So ic goes with what? 8, okay? So it goes with 8, so that's phosphate. What's phosphate? PO4 3 minus. So the formula for the acid? H3PO4. Because to make it a neutral compound, right, you have to have 3 positives over 3 negatives. So there's a couple of different ways you can remember some of this. I'll get back to it in a second, but let's see, white mouse 8, icky cheese, Ite goes to 8. Wait, sorry. Ite goes to us. See, I don't use these. So Ite goes to us and 8 goes to ic. So Ite and us go together and 8 and ic go together. So if you want to remember that, the white mouse 8 cheese, yeah. But that doesn't help us with the hydros. So hydroiodic. You see hydro in the front, you automatically know it's monatomic, right? So it's iodide And the formula for the acid, that's I minus, that's HI. Okay. And then acetic is 8. So that's acetate. That's C2H3O2 minus. So that's HC2H3O2, like that. So that's the process you'll go through when you're going from the name of the acid to formula. In time, you won't write all that out. You'll just know. But that's how we do it, okay? Just practice it. Practice it, practice it, and it'll become second nature. Mm-hmm. Oh, because if you memorize the little block, the 8s, the phosphorus is the, how did you memorize that? T43. Yeah, well, it's part of the field. That's fine. Okay. So one of the things I have to talk about a little bit, because it's part of the nomenclature, sometimes we have what are called acid anions. So an acid has H in the front, right? This is phosphoric acid. But acid ions have H in the front, but they have a charge. So we call them acid ions. They look like acids, but they're ions, so that's all we do. When you have an acid ion that looks like this, you have to actually say how many hydrogens are in the structure. So this one becomes dihydrogen phosphate. Essentially, you're naming it like it's molecular, but it's not, right? Carbonic acid looks like this. So the acid ion, one of the acid ions looks like that. It only has the one acid ion. What would this is carbonic acid. What would I call this? Hydrogen. What is this ion called? Carbonate. Hydrogen carbonate. The other real common name for this, and believe it or not, this is one of the few arguments that my wife and I have. And I'm recording this, probably shouldn't have said that out loud. But yeah, she says it's not necessary for you to know that it's bicarbonate. But that's the other name. If you have one of two hydrogens, like bisect, like you draw a line and cut it in half, it's one of two hydrogens, so bicarbonate. So like baking soda, when you look at the label, it's sodium bicarbonate. It's a sodium with the bicarbonate ion on it. So I really want you to know that. If you watch my wife's videos, she'll say, don't need to know this. But this is not her class. So we have arguments about stuff like this. So, yeah, so hydrogen carbonate is this guy here. What about this? What would I call that? So, what is SO3 minus? Sulfite, right? So this is bisulfite. And you'll see that as an ingredient in different things, bisulfite. It's also known as hydrogen sulfite. So yeah, so the hydrogen literally, it's not hydro, the hydrogen literally means it's a hydrogen. Oh, bi means like bicep, like cut in half. It's normally two. I took one off, so I have half the hydrogen. I should.
Okay.
That's where the bi.
Okay.
See what's. Oh yeah. So just a summary. This is actually from your book, but I have just to help you out. Most people don't think like in a decision tree. Most people just recognize patterns and apply them. But the way this decision tree works is like this, right? Contains a metal or NH4. Well, NH4 plus, that's an ion. If it does, right, this is ionic. This is the first part in the decision of naming a compound. If it doesn't, then it's molecular. If it's ionic, is it type 1? If the answer is no, then you have to calculate an oxidation number, and then the name is still cation plus anion. That's what we just did. And then if the answer up here is no, then it's molecular, so you'll use prefixes. But it says if it starts with an H, and the answer is yes, you name it as an acid, otherwise it's just a binary. Okay, so remember last time we had things like SO2, sulfur dioxide, or CO2, carbon dioxide. This is actually the decision tree, like how you decide how you're going to name it. If it has an ion in it, then it's ionic, and you look at type 1 or type 2. If it doesn't have a metal or an ion in it, then it's molecular, and then you'll either name it as a binary, like down here, or as an acid, like we just did just now. Hydrates are some weird thing that's kind of in between. So we're going to take our first break here. Right, it's only been a little while. Haven't been the full class time yet, but we'll pause because the next part is going to be lots of calculations. And so we'll stop here. Here we go. Let's lecture some more. So we're going to be talking very quickly. Let's review formula or molar mass, right? When you have a chemical compound and you want to know what the formula or molecular mass is, you take the number of atoms of the first element, you multiply it times the atomic mass, etc. You do that for the second element, third element. So that's how we do molar mass. I'm just saying that because we did that at the very end of the last chapter, right? And I just want to make sure we know we're on the same page. Also, as part of the molar mass calculations and atoms and molecules calculations, right? You can use the molar mass to go from grams to moles or moles to grams, either direction. It just depends, like what you put on the top and what you put on the bottom. So for example, if I had water and I want to know what its molar mass is, it's 2 times the hydrogens plus 1 times the oxygen, right? That'll give me 2 times 1.008 plus 16.00, so that becomes 18.016, and that's in atomic mass units, but that's the same as grams per mole, so I could treat that as 18.016 grams per mole. Now, if I want to go and convert from grams to moles, then I need to make sure the gram is at the bottom and the mole is at the top. All right, and the number goes with the grams. If I want to go from moles to grams, it's the same number. All right, I just make sure what's on the bottom and what's on the top. What goes on the bottom for this one?
Moles.
Moles, right? And the number 1, if you want to put the number 1, that's what's there. I just don't write it. And on the top, I need to have grams. And the number goes with what? The 18.016 goes with the grams always, okay? All right, and so when you do that, units will cancel. Grams cancels on this one, leaves me with moles. Moles cancel on this one, leaves me with grams. The other conversion that you need to know how to do, but which honestly chemists use very infrequently, is to go from atoms to moles. This is moles. Or molecules to moles. Since we're talking about molecules. Okay. And if you remember, Avogadro's number is 6.022 times 10 to the 23rd sort of units per mole. So if I'm going from atoms to moles of atoms, I want moles on the top again. And I have 6.022 times 10 to the 23rd atoms at the bottom. And that'll give me moles of atoms. Again, atoms will cancel, leaving me with the units of moles. If I'm doing molecules, it's the exact same calculation. I'll put moles at the top, and I have 6.022 times 10 to the 23rd molecules. Like, I think I said this before, if you're going to write, if it's molecules, write it out, because if you abbreviate it, it looks just like moles. Right? And the moles will cancel, molecules will cancel out, leaving you with moles. Same thing on this side. If you're going from moles to atoms, then you need the mole at the bottom. And then the Avogadro's number goes with the top unit. So it's 6.022 times 10 to the 23rd. In this case, it would be atoms. Okay? So the Avogadro's number, unlike molar mass, applies to everything. Molar mass specifically is for one compound.
So does it matter if they like put molecules or atoms? Like,
No, because, okay, a dozen cats and a dozen elephants, right?
Yes.
Both have how many?
A dozen.
Yes, 12, right?
Yes.
Just one's really big, one's really small. So the elephants are like the molecules. There's a whole bunch of stuff there. But like cats. Did I say cat? What did I say?
Yeah.
Cats. I don't know why I picked cats. Well, because there's probably a bowl of cats around here. But the cats is like the atoms, right? There's a lot of little ones, right? But it doesn't matter. You can't, unfortunately, be really cool if you could just shove a bunch of cats together and get elephants, but you can't do that. So. I like the idea, though. That's the kind of stuff that just makes me laugh. Okay, one of the things we need to learn how to do is calculate the percent composition by mass. And you can either do that from data, or you can do that from the chemical formula. So what we're going to do is we're going to calculate the mass percent of hydrogen in water, and then I'll have you calculate the mass percent of carbon in carbon dioxide. So the mass percent of hydrogen in water, I already know the molar mass of water is 18.016 grams per mole.
Excuse me. How did you know that?
Just from the last one.
Oh, wow.
Yeah, last slide. Last slide or two. Oh my God, what did I just do? Yeah, from up here somewhere.
Oh, yes.
Yeah. So that's the whole. So if I want to know the percent hydrogen, right? The mass percent of hydrogen would be 2 times 1.016. Is that what it is? No, 008. 008 grams per mole, or AMUs, it doesn't really matter what unit you use, divided by 18.016 grams per mole. Oh, times 100. And that should give you 11.19%.
You want us to move the best, like,
No, just multiply by 100.
Okay.
Yeah. Most of the time they show the equation like that, but if you punch the percent button into your calculator, it'll move it over to places you want.
okay. So it's R divided by 12, or R
The part? Oh, because I want to know for the formula for water, right? It's H2O. So the part, that's the hydrogen. So I need 2 hydrogens. For the mass percent of hydrogen in water, there's 2 hydrogens H2O. Yeah, and that's the molar mass of hydrogen. Yeah. Little side note that's super helpful, and I don't know why, but it is. if you memorize the molar masses of like hydrogen, carbon, nitrogen, and oxygen, for some reason, just memorizing those, every time you see them, you don't have to think, what is that? And every time you have to use them, you don't have to look it up. And you use carbon, nitrogen, oxygen, and hydrogen in so many compounds, it saves you like, you know, a few seconds every time, but you do 1,000 times, it's a few thousand seconds you're saving. So. Hydrogen, carbon, nitrogen, and oxygen. I used to always have my students memorize that, and then I thought, I'm not going to do that anymore, but I think it really helps. I, in fact, was so obsessive about it as I was actually cover up the masses on all the periodic tables in the room, and so they just had to have it memorized. Then the teachers got mad at me, so I stopped doing it. Okay, so now seeing like this, here's carbon dioxide. We're going to calculate the mass percent of carbon dioxide. So we need to calculate the whole, that's the CO2. So we have carbon, right? 1 times the carbon plus 2 times the oxygen. That's 12.01. I think your periodic table says 12.01. Plus 2 times 16.00. So that gives me, what does it give me? 48? 44. Yeah, 44.01 grams per mole. So that's the whole. And to calculate the mass percent of carbon, it's 12. Let me write it symbolically. It's the mass of carbon divided by CO2 times 100. So that's going to be 12.01, because there's only one of them, grams per mole, divided by 44.01 grams per mole times 100. That comes out to be 27.2899%. No, I could do the mass percent of oxygen too. It will be 2 times the number of oxygen. Yeah. Yes, the percentage. Yeah. Yeah. In fact, when they say calculate the mass percent of a compound, mass percentages of a compound, then you have to do every single one. Right? But if they say mass percent of carbon in carbon dioxide, you just do the carbon. Yeah. Yeah.
So the masses on this periodic table, they're like not consistent. Like some is for the 1,000 place and some is into 100 place. Like
just use the one that's. This is essentially the same as your book. I think.
Mm-hmm.
Just use that one.
Okay.
Yeah. She was asking like which periodic table do you use, and usually they differ like in the hundreds place or the thousands place because of rounding. And I just said just use the one in your book, and I think that's to the hundredths place except for hydrogen. I haven't looked in a while though, so I used to just always say, well, whichever one has more digits, you use that one, right? That's the most accurate one. Okay, so how do we use percent compositions, right? One thing that you can use it for is you can use it to calculate the mass of hydrogen in total in a mass of water. So let's say I have 35.34 grams of water, and I want to know how much hydrogen that is by mass, just the hydrogen, okay? So I have this 11.19. This is what I calculated from earlier, right? And I could say what this actually means is there's 11.19 grams of hydrogen for every 100 grams of water. That's what the percent means. It's per 100, right? So now what I can use this is my conversion between hydrogen and water. And so I could say 35.34 grams of water times 11.19 grams of hydrogen for every 100 grams of H2O. And I can get the grams of hydrogen will cancel out and leave me with, or grams of water will cancel out and just leave me with grams of hydrogen. What do you get?
3.954.
3.59.
3.95.
95. Yeah, there we go. 95.
4546.
All right, yeah, we got to stop somewhere, right?
Yeah.
Grams of hydrogen. So how many sig figs should be in that answer? Well, it's 4, my percent, 4 in there, so I should round that to 4. So the 4 sig figs, it'll be to here, so it's 3.955 grams of hydrogen with sig figs, right?
Is the 100 mathematic?
The 100 is what percent means,
Yes.
right? Per cent means 100. Century, like 100, right?
But it's only 1 sig fig.
Oh, yeah, I see what you mean for sig figs. Yeah, because per 100 means exact, for every 100 exactly,
Oh, so
right?
this exact thing.
Yeah,
You have to count.
you don't have to count it.
Okay.
Correct. So you guys do the calculation of the percent of carbon in 16.54 grams of carbon dioxide. I'll write it out, and you write it out and calculate it and see if we get the same thing. Double check here. I think I might have fat fingered that. Nope, it's the same. Okay, is that what you guys got?
Yep. Yes.
Oh, here's a fun one. Just a second. We'll do it again. We'll do some more time. I get sidetracked. I have these funny little calculations. Oh, I want to do this one. No, never mind. Yeah, so you should have got 4.514, rounding to 4 sig figs. Oh, we're stop check. And the test is a week from today. And it covers everything through the end of chapter 3. That's why I'm going to finish it all today. Okay, so it turns out that if you're given the information of grams of substance in a compound, that you can figure out the likely empirical formula for the compound. Okay. So, you know, if you have a formula, for example, that's like CH2 or CH4, what does that mean? There's 1 carbon and 4 hydrogens, right? So in fact, it's giving you the ratios of moles of carbon to moles of hydrogen. So if I gave you data that was 21.41 grams of carbon and 3.593 grams of hydrogen, and said that came from 1 compound. Right? So I took the compound, I decomposed it, I got carbon, I got hydrogen. If I figure out the moles of carbon and the moles of hydrogen, I can figure out what those mole ratios are. I can figure out the relative number of moles of each element in the compound and get its formula that way. So what we're going to do in this problem is we're going to take the grams of carbon and do exactly what I said. We're going to convert it to moles of carbon. We're going to take the grams of hydrogen and convert it to moles of hydrogen. And we're going to try to figure out the moles of each element in the compound. And this is the process known as finding the empirical formula. Okay, so we're going to find the empirical formula. So I set it up on the next slide. How am I going to convert 21.41 grams of carbon to moles of carbon? Right? Look at the molar mass on the periodic table. Put your good glasses on. Sorry. You guys are wearing glasses. Yep, so I'm going to go like this. It's 12.011 grams of carbon for every 1 mole of carbon. And I set that up so the grams will cancel like this. Okay, so somebody do that calculation. 1 point, what? Sig figs, I have 4, so I'm just going to put a line there, not round it yet, just use that, and that's moles of carbon, right? Now, when I do the grams of hydrogen, I'm going to convert that as well, because I need to know the relative number of moles of each, right? Exact same process, but whose molar mass do I use? I use hydrogen, so I go up on the periodic table, and you say 1 mole of hydrogen, and then your periodic table says 1.008, I believe, 1.008 grams of hydrogen. You can use a more precise, accurate value if you want to. It'll still come out to be the same. Run that calculation real quick, and what do you get? 4 sig figs, that's moles of hydrogen, right? What? What was it?
3.56448.
That's fine. Doesn't really matter. I wasn't really offended. I just wanted. It doesn't matter. Okay, so now I need the mole ratio. So does that look like anything to you? It kind of looks like it could be 2 hydrogens for every carbon, right? Kind of looks that way. How would you know what it is? You divide one by the other. That'll tell you what it is. So typically you divide by the smallest. Okay. So if just out of form, you're going to do 1.7825 moles of carbon, and that's going to give you 1 exactly. And that's 1 mole of carbon for every mole of carbon, which is kind of a stupid thing, but just have to say it. That's what it is. It's like you're always going to have 1 mole of something for itself, right? There's 1 mole of me for every mole of me, that kind of thing. But what's the other one going to be?
1.1997.
So this is going to be 1.99. Is there another 9?
397.
Whoo! And that's moles of carbon for every, moles of hydrogen, right? For every mole of carbon. And what that really looks like is what? 2 to 1. I mean, you kind of see it in the data when you do the calculation, but it looks like a 2 to 1. So I know in the formula there's actually 1 carbon and 2 hydrogens. That's what that ratio tells me. Now, could it be this too? Right? Because that's still 2 to 1. It's a 2 to 1 ratio. But what this calculation actually does is it can't tell exact numbers, it can only tell ratios of numbers. And when it comes down to it, you only figure out the empirical formula this way. Coincidentally, sometimes it is the molecular formula. And remember, the empirical formula is the smallest whole number ratios. It could be that it's C2H4, or it could be C3H6. It could be a bunch of different things, but we don't know. Okay. This would be a possible molecular formula. So could C3H6, because those are all 2 to 1. The information you need to know to figure that out is you need to know how much the molecule actually weighs, or actually how many of these empirical formulas go into the molecule. So if I knew how much the molecule actually weighed, I can calculate the mass of this and figure out how many times it goes into it, and that would tell me what the molecular formula is. And for your practicing pleasure, go ahead and figure out empirical formula for this. I will be silently writing up here while you guys work on it. All right. And you could look up periodically to see if you're doing that correctly. Oh no, I got it backwards. O to N. Oh. What's that? Oh no, because you always divide. You're looking at the ratios of the two. So you're always dividing by the smallest number of moles. So I want to know. Like I know there's one. I know that nitrogen. Oh, I'm pointing here. Hang on, sorry. I'm not used to having this. I know that there's 1.85 moles of nitrogen in the compound. At least these parts right? And then I know there's 4.628 moles of oxygen. But I need to know the mole ratio of nitrogen to oxygen, or oxygen to nitrogen, and all that in good form. When I look at this, I notice that this is the smaller of the two, so I divided both by this. I know this is going to come out to be 1. There's always one that's that one. But this one, I want to specifically know moles of oxygen to moles of nitrogen to get my mole ratios of the elements in the compound. Yeah, so let me write my last little note on here. Last little note on here is this is dividing by the smallest. And that's what I'm doing. I'm dividing both by the smallest. So I end up with this number 2.5 to 1. Well, yeah, it's 2.5 oxygen. Yeah, so here's the thing. Let's write that. Okay. Well, hang on. She's like all mad at me already. We're not married. Take it easy. Sorry. So now it looks like N1O2.5, right? That's what it looks like. Can you have half an oxygen?
No.
Okay, so I'm going to double it. I'm going to multiply by 2, right? And when I do that, that comes out, the ratio 2.5 to 1 is the same as 5 to 2, or 2 to 5. So I have to get rid, this needs to be whole numbers. That means multiply by 2.
Is it always 2 or is it?
No, it can be 3, it can be 4, it could be 5. Hang on. Yeah, so the very good question is, how do you know what to multiply it by? Well, if you see a 0.5 and you want to get 0.5 to a whole number, what do you multiply it by? 2. If you see a 0.333 and you want to get it to a whole number, what do you multiply it by? If you see a 0.141. I don't know. Just multiply by 7. How did I know that? That's the reciprocal of 7. So this fraction is always a reciprocal of some number. Right? That's like the way. Now, what I always tell my, so that means you just take that number, invert it. That tells you what the half, not the whole part, just the fractional part. Multiply, you invert that, and it'll tell you what number to multiply by. Now, my Chem 3A students, this is what I always tell them. If it doesn't, if it's not one you can tell, well, try multiplying it by any number. Start with, usually you can see a half, you can see a third, and a quarter. And then you get to a fifth, and a sixth, and a seventh. Sixth and the seventh, people don't know. Right? Just multiply by 6, and multiply by 7. Well, it gives you a whole number, that's what you were supposed to multiply by. Right? But yeah, the fraction, for my Chem 1A students, I tell them the fractional part is the reciprocal of some number. Take the reciprocal, and that'll tell you what the thing is you multiply by.
I think the reciprocal on the front.
1 divided by, oh, on this, 10 to the minus 1. Take it to the 1 power. Minus 1 power. So, no, sorry. Take 3.5. Oh, wait, sorry. Back up. You just want the 0.5.
0.5?
Yeah, it's the 0.5. And it's to the minus 1 power. So you have to raise it to, let's see what it went here, -1. Or you could just say 1 divided by 0.5. That's the reciprocal, right? Yeah, so either way. Okay. Actually, I'm going to, I'll just use this as. So if you have the molar mass, this is what I was talking about before. When you do this calculation, you always get the empirical formula. If you want to know what the molecular formula is, you need to know the molar mass. So if you have the molar mass, you take the molar mass, you take the empirical formula mass and you divide it, and it'll tell you how many times it goes into it. Like 2, 3, 4 times. And then you can figure out what the molecular formula is. Okay, so I said that before. Here's an example, right? Compound has a molar mass of 56.11 grams per mole and an empirical formula of CH2. Determine the molecular formula. So this actually goes along with that earlier example. And I go, well, molar mass. Oh, you know what? Yeah, that's right. I would go like this. I need to know CH2's mass. So that's 1 times the carbon plus 2 times the hydrogen, right? That comes out to 12.01 plus 2 times 1.008. That comes out to 14.028. And that's the last sig fig there. And that's in units of grams per mole or atomic mass units. It doesn't really matter. Okay. And then to calculate the N is going to be 56.11 grams per mole divided by 14.028 grams per mole. Gee, I hope this comes out to a good number. Doesn't look like it to my eye. How am I going to know if that's a whole number? It's the number of times the empirical formula it divides evenly into the molecular formula. Yeah, I'll show you how to use it in a second. We're just going to calculate it and then I'll show you the formula. I probably should have showed you first. So I'm going to take 56.11 divided by 14.208, 3.95, right? I get 3.949. I'm going to assume that that is 4 times. It needs to be a whole number. Okay? So that means what I did, and you could double check my calculation in case I screwed up. So if I have the empirical formula as CH2, 4 times that gives me C4H8. That's how you use the N. The N is the number of times you multiply the formula you get with that. That is a weird one though. C4H8, what is that? Is it 3.999? Oh yeah, I fat fingered it then. I thought it was closer to 4. Just like I said, it's 3.999. Oh, is equal to 4. It's 4 times. Because 3.999 is about 4. Yeah, so the idea is this is how much the molecule weighs, but this is what you got as the empirical formula. Right? And so if you can figure out how many times this goes into the molecular mass, that tells you how many times the empirical formula goes into the molecular mass. So there's 4 of these together make the molecular formula. So you just multiply all the subscripts by 4. How many more slides do I have? I'm just curious. Oh my God, we're almost done. Oh, you know what I didn't do? Yeah, I'll pass on it for now. I did, huh? I did. We didn't do what?
What didn't you do?
Oh, I know what I didn't do. I forgot to do a problem if I give you the mass percents to an empirical formula. I'll have to show you that. I'll show you that later. But okay, so how do we figure out these formulas anyway? Right? It's one of those things that 1A students kind of need to know. So it's pretty simple. If we have a hydrocarbon, anything can carbon, hydrogen, oxygen. This is where we start. We can do nitrogen, sulfur. There's other ways to do this with other elements. But the simplest one to understand is carbon, hydrogen, and oxygen. Basically, to figure out, okay, the amount of carbon and hydrogen that are in the compound is we burn it. Okay? So what is combustion? Combustion, you take oxygen, right? And you take the compound and you burn it and you get carbon dioxide and water. This is the process. The reaction we're depending on just says, I have this compound CHNO. I'm burning it in oxygen. And I'm going to get CO2 and H2O out of it. And this is what we do. We have an absorber, a desiccant really, for the water vapor. So you burn it, the water vapor gets trapped in here. And then the CO2, we have a carbon dioxide absorber as well. And it gets trapped in here. Same thing like in the space shuttle, they used to remove the CO2 from the atmosphere. It's the same kind of chemistry. So here's the deal. If we weighed these before, and then we burn the sample, and the gas comes through these tubes, right? This will have all the water. So I've weighed before and after without telling me how much water mass is in the sample. I weigh this before and after, and I'm telling me how much CO2 is if the carbon is in the sample. Like CO2 only, carbon only comes from the compound. So I can use the carbon dioxide mass and the water mass to figure out what the empirical formula is. that make sense? I'm going to burn it, I'm going to capture those two things. Those will tell me the carbon and the hydrogen, it turns out. Now think about an unknown, right? Here's the problem of an unknown. This is actually ethyl alcohol. It's not really unknown. Pretend it's unknown. And I'm burning it with oxygen. And I use an excess of oxygen. So I use pure oxygen in this process. Just pure oxygen. And when it burns, it gives me carbon dioxide. And you know, ethyl alcohol has 2 carbons in it. So I'll get 2 carbon dioxides out for every one of these. So 2 moles of carbon dioxide for every mole of water. I mean, every mole of unknown in this case. For the hydrogens, right, these go into the waters. So there's actually 6 hydrogens on this compound. For every molecule, I'll get 3 water molecules. And then there's going to be leftover oxygen because we burned this thing with an excess of pure oxygen to get it to burn well. Okay? And as a result, here's the weird thing. If there's a water molecule in here, one of these oxygens in here, I mean there's a oxygen in here, one of these oxygens in here, or here, right, could have come from the original compound. So we don't know entirely like how much oxygen was in the original compound because it comes from here, and it ends up in one of these. So this is what we do, okay, just so you can get the idea. If I could figure out how much carbon is in here by mass, if I can figure out how much hydrogen there is in here by mass, I can actually take the carbon and hydrogen mass and subtract it from what I start with, and that'll be the top. So the process is going to look something like this. I'll have a mass for this, and then I'm going to have a mass for CO2, and I'll have a mass for water. And this is going to be the mass of the unknown, so I'll just put U there for the unknown. From the mass of the CO2, I'm going to get the mass of carbon. And from the mass of the water, I'll get the mass of the hydrogen. And the way I'll do that is I'll just use the mass percentages that I've calculated already to calculate how much there is. So if I know that I have 10 grams of water, I know 11.19%. That's the percentage we calculated before. That much of it is hydrogen, right? So if I take the mass of the unknown, that's equal to the mass of the carbon plus the mass of the hydrogen plus the mass of the oxygen, right? I know all these. Those are known. I can solve it. So I will have mass of oxygen is going to be equal to the mass of the unknown minus the mass of the carbon minus the mass of the hydrogen. And then after all that, I can convert them into moles and calculate mole ratios. Right? So I'm just trying to get to masses. So we're going to do a problem so you can see how it's done. Now, just so you know, right, we're going to calculate the carbon from the CO2. This is what I was just writing. I did it on the picture. We're going to get the carbon from the CO2. We're going to get the hydrogen from the H2O. And then we're going to get the mass of the oxygen by subtracting the mass of the carbon and the mass of the hydrogen from the unknown. Oh, that's an H. Yeah. It did look like an H if you zoomed way in. Like it was like this, it probably looked like that. I'm going to show you. Now, there's 2 ways actually you could do this. Actually, you could calculate percent composition from the numbers that you have, but we're just going to do straight mass to mole conversions. Okay. So here's some combustion data. And this is the percent information from the mass percent calculations earlier. So we calculated those on an earlier slide. And I like reusing things so we don't have to think so hard about where to take them. That's from earlier. That's CO2. I want to know how much carbon is in that CO2 from the combustion analysis. All right, so this is all I'm going to do. I'm going to go this. I should have left more space in between there. It's going to be 27.289 grams of carbon for every 100 grams of CO2. And I'll get a number for that. Somebody else better get a number for that because I don't have a real calculator. Say it again. 0. Wait. What's the number? 0.40624.
24.
Oh. There's an 8. Yeah, I better keep it. I need 5 sig figs. This is grams of carbon because the 100 gram, this cancels here. That's grams. So for the water, what am I going to do? Just multiply by 11.190 divided by 100. And then what do I get? Eight. So this is what we're going to do. We're add those two together. And then add those two and tell me what you get. Two 8.096. Is that what you said?
Yes.
That's the grams of the hydrogen plus the grams of the carbon, right? So look at that number, right? That's not what it started. It started out as 0.440 grams. The rest of the mass is the oxygen. The grams of hydrogen, the grams of carbon, and the grams of oxygen need to add to be the total. They're not close to the total, so the rest of the mass must be oxygen. So you figure out that by just subtracting, right? So the grams of oxygen going to be the 0.440 grams total. That's the grams of the unknown, right? Minus 0.28096 and grams. And what do you get for that? Negative. 0.44 is bigger than 0.28.
Oh, I put a 2. My bad.
I get what? 15. I have water. My ears. 90? Yeah. I've had like fluid in this ear for like, I don't know, half the summer. So people talk to me and I'm like, can't hear you, sorry. They'll be like right in front of me. Like, talk louder, I'm getting old. Okay, so this is a different process. So before we divide and figure out how many moles there are, we have to figure out how many grams we have. This is like empirical combustion analysis, the first step, just figure out this mass. And now we can convert it to moles. Okay, so now I actually wrote all that out. That's the process for that. I'm just going to do these 2 slides, right, I'm just going to do them all right here. Sorry. So now we're going to set up our table. We need to figure out moles, and then we need to figure out mole ratios. Okay. So we're going to start with grams. So I'm going to go grams of carbon. I'm going to start with that. 0.24068 grams of carbon. Then I'm going to have, so you could be writing on the next slides if you need space. It just makes more sense to me to do it all right here, right now. I think what, yeah, now we're doing the empirical formula. So I have grams, I'll have carbon, hydrogen, 0.04028 grams of hydrogen. These both have 4 sig figs. And then I have 0.1590 grams of oxygen. This is the mass. We're going to put the moles over here. I'll put the moles right next to it, actually. And then we'll do the ratio. Now, to go from mass to moles, we're going to be dividing by the molar mass, right? So we're going to go times and then 1 mole over 12.011 grams. And this will be times 1.01 grams for every 1 mole. Or 1.008 grams. And then oxygen will be 1 mole for every 16.00 grams. And those are just molar masses off the periodic table. And remember what I said? Those are really good ones to memorize. Yeah. Because they just come up all the time. And it just makes your life so much smoother to just know those. The grams will cancel in all these instances and we'll be left with moles. So somebody give me the moles. Okay, what's the second one? It's 0.0399. Yeah, and then what's the last one? What'd you get? Oh, okay, well try, that's pretty close. I think that's a rounding difference somewhere. What? It's an extra 1. Oh, yeah. I instead of 12.01, which is in the period in your book, I used a more precise, accurate number. Yeah, sorry, but it'll come out. It'll be the same. It's because of that. 0099. What's the next? Any more digits?
3.
Okay, so to do the ratios, right, you have to divide by the smallest. Which is the smallest?
Oxygen.
The oxygen is, right? So we're going to divide by the oxygen. And I'll go ahead and do this one. I can, this much I can do on this phone calculator. I think I gave my other calculator to my son. So the ratio is 2, right? And this one is 2.00, and this will be 1. Is that what you got? Yeah. So what does the formula come out to be? Well, it's going to be C, right? 2 H 2 O. So that's my empirical formula. By the way, you will for sure get something like this on a test. 4? Okay. This one's 4?
The second one is 4.
Ah, good. And this becomes 4. Okay. So that's the empirical formula, right? Let's do something really quick because it gives you the molar mass, and so we can actually do the molecular formula. How much does C2H4O weigh? What's its molar mass, right? So we're going to get its molar mass. It's going to be 2 times 12.01 plus 4 times 1.008 plus 16.00. And what do you get when you do that calculation? What'd you get?
44.
Oh, 44.052. It's grams per mole. Well, what's its molar mass?
80.
It's 88, right? So what does that mean?
It means that's 2.
There's 2 of those empirical formulas in the molecular form. The molecule weighs that much, 88.0, it's given. But the empirical formula only weighs this much. So there are 2 of these in the molecule. Okay. The way you get that number, though, this should be C4H8O2, like that. But the way you get that multiple times 2, if you don't see it immediately, it's just dividing the masses. This is that N that we used before. N is 88.0 divided by 44.0. That's 2. That's where that number comes from. But sometimes you can just see it, right? Like this one, 44 times 2 is 88. So I knew it was 2 of them. So I would have just written it out. Just double checking. Oh yeah, functional groups. Functional groups, and then we'll do. We'll stop actually and do the study guide. Just about done. Questions? Followed so far? I don't think I left anything major out, except for I should show you how to calculate from percentages as well. Okay, last thing I want to do is this, and then we'll take a break again, and we'll come back and do the worksheet. I will show you one more example after the break. So, hydrocarbons. I want you to know what a hydrocarbon is. What does a hydrocarbon sound like? Hydrogen and carbon. So, hydrocarbons are known as, hydrocarbons are compounds that have only carbon and hydrogen in them. And the number of carbons helps us determine what the name is, okay? So for example, CH4, this is methane. The alkanes are known as saturated hydrocarbons. They all end in A and E. So if you wanted the name of any alkane, you just know how many carbons there are, and you end it in A and E. So if it's butane, right? If you're counting, right? 1, 2, 3, 4. That's C4. It's actually H10, and I'll tell you how to do that in a second. Okay? This is butane. All the alkanes follow this general formula: CnH 2 times N plus 2. So let's say it's pentane. Pentane means 5 carbons, right? So 2 times 5 plus 2 is 12. So pentane's formula is C5H12. Okay? When we do Lewis structures, like why it's that way, it becomes a lot more clear. But for now, it's just a formula. Now, if I take an alkane and I add a different element to it, okay, that element becomes part of what is known as an functional group. So if I have C2H5OH, this is known as an alcohol. Oh, by the way, I should say this, but even though we haven't covered it in the sort of the prerequisite coursework, you should know what a double bond and a triple bond is. So there are alkenes and alkynes. I'm not going to spend much time on it, and I don't care that you haven't known yet, but later I'll expect you to know. Alkenes and alkynes are just double bonds. Amines. All right. Oh, by the way, this is 2 carbons, right? So 2 carbons is what? What's the prefix that would... Eth, right? So it becomes ethanol. Huh? Why not? Okay. If I have C2H5NH2, this functional group, this is an amine. Spell it better. That's actually, its name is, the common name is actually ethylamine. The systematic name is ethanamine. Yeah. But you don't need to know the actual systematic names. I just want you to know what the functional groups are. So that we have alcohols, we have amines. We also have things that are called carboxylic acids, where you replace one of the hydrogens. In all of these, I'm replacing one of the hydrogens with one of these groups. And then there's also aldehydes and ketones, which I don't care about for right now, but we'll do those later. But you'll learn those in the future. But I care that you know that if you replace a hydrogen with an OH, or a hydrogen with an NH2, or a hydrogen with a COOH, those are alcohols. And those functional groups give this is part of organic chemistry, give the molecules its properties. And so if I say, oh, we're going to use this alcohol today, I kind of want you to know generally what an alcohol is, that kind of stuff. All right. Well, it covers it. I will put it again. It's carbon is 57.144%. Hydrogen is 4.96%. Oh, 796. And then oxygen is 38.061%. We're going to find the molecular or the empirical formula. Sorry, this thing's wobbling a lot. I gotta get back on that. There we go. Empirical formula. Okay. And the only thing different about this problem is it's done in percent. So before I gave you grams the whole time. I gave you grams, I gave you grams, I gave you grams. So this is how this problem is different. Different percentages. These are percents by mass. How do you deal with it, right? Well, what if you had 100 grams of this compound? How many grams would be carbon?
57.1.
Yeah, 57.144. So this is what you do. You assume that you have 100 grams. When you're given percentages, just assume you have 100 grams. Because it doesn't matter how much you have, you're still finding the ratios. The ratios will be fixed regardless of how much you start with. Okay? So you say, I have 100 grams, and just replace that with grams. Just like that. And then you're still going to calculate the moles. Right? So we're going to calculate moles. And then we'll do the mole ratios. And then I'm going to teach you about this really cool app that I like to use this point, I think you're probably okay knowing about it. You're probably old enough. Yeah, you're like, what kind of app is this? I'm like,
How did you in college cheat?
It's not cheating. I'm telling you about it.
Help.
Chem 1B is one of the first things I tell them. Oh, Chem, they already know about it because they already have 1B with them. Get this app, it's great. Okay, so we're going to calculate these. Somebody would start rattling off those numbers.
Is it 12.01?
Well, 12.01, 12.011 won't matter.
The first one is the one for carbon, right? 4.758.
Oh, yeah, that first one's carbon, yeah. It's what?
4.7580.
4.7580. That's moles of carbon. And then the hydrogen should be close to 4.6 or something. 4.7579 moles of hydrogen.
Was that for the percent is 4.796?
Yeah.
Okay.
And then what's the next one?
So it's 2.3788.
Oh, you kind of see it already, right? You're looking at those ratios. I mean, we're going to divide it. But you guys see 4.7, 2.3. It's about a 2 to 1. 3758. Now you know what I go through when I grade papers. I'm like, what is that number? I don't know. So we're going to divide by the smallest. This is the smallest, 2.3758. This is 2.3. Oh, it's 88? Oh, it's 88. 88. 2.3788 and 2.3788. This is moles of oxygen that we're dividing by. And I'm going to give away the big secret here. This is 2 moles of carbon for every mole of oxygen. This is 2 moles of hydrogen for every mole of oxygen, and this is going to be 1 down here. So my empirical formula looks like it's C, H, and O. What are the subscripts? 2, 2, and 1. Okay. A lot of times people won't write the subscript at the bottom like this. But as you're doing empirical formulas, it's okay. Normally you don't write it. But when you're doing empirical formulas, just write it. Makes your life happier. So a couple of things different about this example, as I realized as I'm looking back through the examples in my head. This had 3 elements, right? The previous hydrogen combustion one did too. Still, you divide by the smallest. And when you have percentages, the other thing is that assume you have 100 grams, replace the percent with grams and go from there. The exact same kind of problem. And if you want to, you can do this on your own. The molar mass is 168.15. Yeah, you get that, and you'll take that number divided here, so you can get the molecular formula from that. So just a side note, if you're tired of calculating molar masses, there's an app for that. Okay. I love telling you. It's called CMM. You can look it up. They have it on all platforms. It's actually from an environmental chemistry website. I think I used that website before there were apps, so this has been around forever. But you look that up. It stands for what? Calculate molar mass, yeah. And it's all you do. You just type the formula in with your thumbs, and it tells you as you're typing in what the mass is. Right? And then when you're all done, it actually gives you the percent composition information and all that kind of stuff. So it's pretty handy. Huh? CMM. calculate molar mass.
That's a good one.
So consider that a gift from me to you. You can't use it on the test. But up to and actually, like tests after this one, I generally give you molar masses because I don't want you to waste your time calculating molar masses forever. But you should know how to do it by now, so that's why I do that. Just make your life easier.